I'm just passing the buck, because now I'm saying, okay, well, I want to measure delta H as a function of two enthalpies of materials. How the hell do you measure those, each of those, right? Right, so what is H2O gas and what's H2OL? How do you measure those things? Right, well, maybe we want to do another process where we can measure delta H, where one process makes H2O gas that we measure heat, and another process that makes H2O liquid. Right, so for instance, if we have some material A and B, and when it reacts, it forms H2O gas. And maybe we have some other process, C plus D, that makes H2O liquid. And this has an enthalpy HA, and this has an enthalpy HB. And if we can measure the enthalpy difference here, HC, if we can measure that, if we can know all three of these, then we can know HD. Right? Because HD, because of this, let's see. So HD is going to be H2O gas minus H2O liquid. Right? And then delta HA is going to be the enthalpy of H2O gas minus, sorry, this is a minus sign, the sum of the enthalpies of A and B, right? Minus products minus reactants. And we can just keep going down here. HB is H2O, sorry, the enthalpy of H2O liquid minus the enthalpies of C plus D. And then HC is the sum of the enthalpies H, C, and D minus HA plus HB, right? So I've just made a bunch of different reactions that all are just differences of products minus reactants. Now, what I can do is I can take HA, HB, and HC and write HD in terms of them, right? So let's see how that happens, right? So if we add HC to HB, let's do that first. Let's see what happens here. All right, so if we add HC plus HB, right? Notice that the HC and HDs cancel out, right? We lose those. So the sum of these enthalpies that we can measure would be the enthalpy of H2O liquid. Sorry, that's H2O liquid. Minus HA plus HB. That's the other term from HC that's left over. Right? And we can get rid of that term by adding to it HA. Right? So if I take HC plus delta HB plus delta HA, I'm now left with H2O, the H of H2O liquid minus the H of H2O gas. Because the AB in A has canceled out with the AB in C plus B, right? So now if you notice, I have now, if I take the sum of these three steps that I've taken kind of looped around the reaction I want, if I can measure these three, then I get an enthalpy difference of my two products that I wanted to measure in the first place. Now it's flipped from what I want, right? But that's pretty straightforward, right? That just means that this is equal to minus HD. Right? So this is the advantage of using state functions that are only dependent on products and reactants, is that if I have something that I want to measure that's really hard to measure, that I could maybe just go around in a loop and measure three kind of related things that are easier to measure, and then when I add the enthalpies of all those together, I get the enthalpy that I want indirectly. Okay. Right, the term for this concept, and we'll look at it more carefully next class, is called Hess's law. Right, which just says that the enthalpy, the total enthalpy of a reaction or a process is just the difference of the products and the enthalpies of the products minus the enthalpies of the reactants, and I can just chain them together in a linear fashion to cancel things out. All right, so if I can't measure D, I can measure A, B, and C, and then find D that way. This is exactly how the calorimetry lab works in PChem, the PChem lab, this rotation, except there you only have, you're measuring 2 reactions to determine the third. So this can work all the time, and in fact, this is how we typically experimentally measure difficult measurements, difficult heats or enthalpies, by measuring 3 related enthalpies that add together to the one that I want that are easier to measure. Okay? This is kind of the trick that we do to get around hard experiments. Right? We'll see this trick come up multiple times in this class. It's this chaining trick. Okay? You can use this to your advantage and make calculations in thermochemistry much easier to know that you can, instead of doing one big step, you can take 3 small steps to get to the big step instead. Right? You can always kind of split your calculation up one at a time. All right, so, but again, one of the things that we have to consider is how do we make this process easy? Right? The idea is in order to measure this enthalpy change when we vaporize our gas or condense it, we have to know something about A, B, and C, D. Right? So what we should do is pick a series of A's and B's and C's and D's, these intermediates, if you will, that are really easy to define, and they have kind of standard enthalpies that are easy to measure, right? We want to take basically a reference series of molecules that we can use as building blocks thermodynamically to understand the enthalpy of bigger, more complicated molecules. So you can kind of think of this as like a Lego brick approach. We take 3 simple reactions to measure something that's more complicated. Right? So we're going to kind of Lego brick it up. So the question, of course, is what are these standard Lego bricks? Right? What are these A's and these B's and these C's and these D's that allow us basically to maximize our ability and make it easy to start doing these kinds of calculations about energy? Okay? Like a reference, if you will. Some numbers that we know really, really well. Right? So the better we know our intermediates, the easier it is to calculate things that are derived from them. So people have thought about this problem for a long time. And we kind of have a very nice framework for how we define our references for enthalpy. And this is called the IUPAC. Well, this is what I call it. It's the IUPAC enthalpy. Let me call it standard enthalpies of formation. Standard is important here. This is probably not the official term for it, but this is close enough. All right, and these are going to be a set. All right, first of all, IUPAC, if you don't know, is the International Union of Pure and Applied Chemists. It's kind of like the Chemist Illuminati. They make the decisions about what's official in chemistry. They decide nomenclature. You know, the fact that we call things ethane, butane, and pentane, and so on is all determined by IUPAC. They're the ones that tell you that water is dihydrogen monoxide. That's the proper way to call it, if you will. Right? They're the people who decide these things. And the idea is very similar, and it's a global, of course, it's a global Illuminati. So let's talk about the idea of what these are. These are enthalpies that are referenced to a set of standard chemical constituents or chemical components, say chemicals, molecules, atoms, chemical components, that commonly exist at standard temperature and pressure. All right, and I'm going to kind of walk through how this works, okay? So first of all, we have to define what standard temperature and pressure is. So for IUPAC, We call the standard temperature T circle, T naught. And the standard temperature, of course, is 298.15 Kelvin, right? 25C, STP. And the standard pressure that everything is defined at is 1 bar, right? So, which is roughly 1 atmosphere, right? So what we're going to do is we're going to have a standard set of chemical components, think the fundamental building blocks of chemistry, and what we're going to do is we're going to define their enthalpies exactly. And then everything that's more complicated that's built from those standard atoms and molecules are all relative to these standard enthalpies, standard materials. So what we're going to do is that for every, right, so each atom, choose the most common state for each, choose the most common state that exists at T and P. And by state, I mean chemical state. And then for each of those, so for each one of these standard atoms, standard states, we set their enthalpies to be 0, exactly. Okay? The idea is that we're going to come up with a set of, basically we're going to go down the periodic table and look at each atom and say, hey, this is the standard way to make hydrogen, its enthalpy is 0. Okay? And then we'll go to fluorine and say this is the most common form of fluorine at 298 in 1 bar. This component, this material has an enthalpy of 0. Okay, so everything that we create that's more complex will always be referenced relative to these standard enthalpies. All right, we'll see how this works in just a second. So let me show you a resource that will allow us to kind of look at what these standard states are. Right? And it's on Canvas. Let me just pull it up really quickly. We'll look at two different resources today. The current homework doesn't really focus too much on this, but it's going to come into really, really big use for us in the next homework when we talk about equilibrium, where we'll really use these numbers more consistently. So here on, oh, sorry, you can't see that. So here on Canvas, right on Module 0, I have 2 links at the top, chemistry reference material, this NIST webbook and this ATCT active thermochemical tables. Right, so these are really, really nice features for this, really, really nice resources for this class. We'll look at NIST in a second. First, I want to look at this ATCT. Right? If you don't know, NIST is the National Institutes of Standards and Technology. This is a Department of Commerce clearinghouse of chemical information. Okay, this is kind of like the official U.S. government chemical repository. And ATCT is also a government project. It's run by a group out of the Department of Energy. Click this. In fact, when I was at Argonne National Lab, my neighbor was the head of this. His name's Branko Rusic. He's an old Croatian chemist who's been studying thermochemistry, enthalpies of stuff for many years. He's one of the most biggest experts in this concept, this thing. And he's one of those guys who determines what these enthalpies are. Right? He's the one who comes up with the numbers. He's the king. So he's got this website where he lists the most accurate enthalpies for every material. These are our reference heats for all of our different chemicals, common chemicals. And let's go down the list here at the top. As you'll see if you go on this website, they get more complicated as we go down. Right, and let's just kind of look through like the most common atoms here, right? H2, He, carbon, N2, O2, F2, Ne, silicon, liquid, crystalline liquid, sulfur, crystalline, chlorine gas, argon gas, bromine liquid, krypton gas. Right? These are the most common forms. This is how you find each of these atoms are the most common forms of these atoms at room temperature and room pressure. Right? Remember H, for instance, hydrogen is an H2. So, well, and as you can see here, we can look at the enthalpies here. So these are the reference enthalpies for each of these components. And as you can see, they're all exactly 0. All exactly 0. Right? So these are our standard states. Okay? So anything that we want to think about the heat of, say for instance, we want to blow up a hydrocarbon, we want to combust it, and we want to figure out how much energy that fuel provides, we're always going to reference our hydrocarbon back to H2 and graphite. Right? These are our standard states for carbon and hydrogen. I'll show you an example of that in a second. So anyway, you can go down this list. I'll just keep going, and you'll see there's just a bunch of things that are 0. And again, each atom has its own reference state. And there's only the most common ones on this website. But you can see all of these are 0. All right, and then the moment we come down, let's go to hydrogen atom. I think this one's very interesting. All right, this is just hydrogen by itself. All right, it says its enthalpy is 217.998. All right, so it has a non-zero enthalpy. Why is that? Well, let me show you why. So let's just do a quick example. All right, let's think about the enthalpy of taking H2 gas and splitting it, what we call a homolytic cleavage, into 2 hydrogen atoms. Okay, what's the enthalpy? What is the heat of this reaction? Well, remember the way we will do this, delta H is the H of the products minus H of the reactants. Okay, and the products here is going to be the enthalpy of H. Right? Let's go really quickly. I just want to Alt-Tab back. If you notice, these units are in kilojoules per mole. Okay, so this number is per mole of hydrogen. And our stoichiometry is 2 moles of hydrogen, so I need to multiply this by 2. And then from that, I subtract the enthalpy, the reference enthalpy for H2. Okay, and so by definition, remember H2, molecular hydrogen, is the standard state for hydrogen at room temperature and pressure. Right? So this is by this term right here is by definition 0. Right? So that means that the enthalpy of the reaction is 2 times the enthalpy of hydrogen. And that number is, just highlight it, 217.998. So this is 2 times roughly 218 kilojoules per mole, which is 436 kilojoules per mole. What does this number tell us? Well, very simple, right? We're looking at a gas and we're dissociating to a gas. There's very little PV work, right? So all of the energy change is pretty much heat. So what this is telling us is that it takes you have to input 436 kilojoules per mole of energy into your gas to break apart H2, right? That's how much energy it takes to break that bond, right? So all this is just the bond strength of hydrogen, right? This just tells you how strong this bond is. That's all this number is telling you. Right? This is roughly the HH bond strength. Right? So that's an endothermic reaction, right? You have to put energy in, and you have to put 436 to break that bond. Okay. I want to, let's just really quickly, I just want to define these terms for you on the side because I just used it and you may not know them. But let's just remember I'm going to use these terms a lot in this class, so let's just remind ourselves the difference between endothermic. This means, again, delta H is greater than 0, and that means system absorbs heat from the outside. From environment. Right, you have to supply it heat to get this to go. And then, of course, exothermic is the opposite. It releases heat. Sorry, not from environment, to environment. So just a reminder what those terms mean, just in case, because I use them a lot. Another way to interpret this, right? So one thing is I said that it takes 436 kilojoules per mole to break a hydrogen bond, a HH bond, which is 100% true. Another way to think about this is that the two hydrogen state, the state of the box where you have 2 mole equivalent of hydrogen atoms, is 436 kilojoules per mole less stable than H2. Right, so what does that mean? That means that when, just think about the reverse reaction, right? The reverse reaction is when 2 H molecules come together, 2 H atoms come together to reform H2. That's a stabilizing interaction because you form a bond, and when that happens, it releases 436 kilojoules per mole. Right? So the enthalpy tells you something about relative stability. Now, the term stability is we have to be careful with because stability implies something about time, right? Something that's stable is something that lasts a long time. And how long H atoms last depends on the conditions of the system. Right? H atoms may be very stable. In fact, they're extremely stable in the cold universe, out in the middle of nowhere where there's no gas or anything, a vacuum. H atoms are perfectly fine. But if you're in a condensed gas, here on Earth, you have a bar of pressure, H atoms aren't very stable, and they'll more than likely hit each other, form H2, and then release energy in the form of this 436 kilojoules per mole. Okay, so this number gives us something about stability a little bit. Think about this state is, H2 state is lower, the box is lower in energy with H2 than it is with H. So you have to raise the energy of the material in the box to get to a state that has 2 hydrogen atoms in it instead of an H2 molecule. All right, it's another way to think about this. All right, one more thing I want to show you on this page, and we'll come back to this page as we do more examples over the next couple of weeks, is that there are 2 columns here for delta H for each one. And let's look at their labels. Notice that there are 2, right? One is at 0 Kelvin and one's at room temperature. Okay? Are they different? Let's go back down to hydrogen. Let's just kind of look at a series of them. And you'll notice that the enthalpy, the standard enthalpy for these molecules, changes whether the system's at 0 Kelvin, right, which means that the box has no heat, right? And then when you put 200, 300 Kelvin of thermal energy into the box, you can see that the enthalpies change. So what's happening is you think about the stability of the box, right? The energy of the box in some condition. Say, for instance, if it has H2O gas in it. If you have a box of just H2O gas, the energy of the box at minus 238 is minus 238 kilojoules per mole. And then you start to heat it to 300 kilojoules per mole, and the total energy of the box drops by almost 4 kilojoules per mole, and now it's 241.8. Right? Why is that? Or why is it that these enthalpies change as a function of temperature? Right? When we're talking about how these enthalpies, right, these enthalpies have something to do with the strength of the bonds that you're forming relative to the standard state, right? This enthalpy, which is negative for H2O, tells you, right, what's the standard state of forming H2O? Well, it's a molecule of one molecule of O2 and 2 molecules of H2 mixed together in the gas phase to make H2O gas. That's the O2 and H2 are the standards. So this tells you that a box of H2O gas is 286 kilojoules per mole more stable than a box of H2 and O2, mole equivalent. But for some reason, that stability changes as a function of temperature. Right? Why is that? Right? So one thing is that when we calculate heats of reaction, what this tells us is that, say, for instance, taking water from gas to liquid or liquid to gas, that value of that heat release is going to change depending on what temperature you're at. Right? So at one temperature, it might absorb more heat, and other temperatures, it might absorb less heat. Right? Why is that? Right? So we have to look at that more carefully. Right? When you do enthalpies and stuff in Gen Chem class, you're almost always given these standard reference enthalpies, right, at 298 Kelvin. But if you're doing a reaction at 500 Kelvin, those numbers are going to be wrong. Right? So we have to think about, well, how do we account for this difference, and how do we predict what an enthalpy will be at a certain temperature? Right? Because if we want to accurately measure how much energy our system does, we better get a good prediction of it at the temperature we're doing the reaction at. Okay, before I start that, I'm just going to add one more term here. I'm just going to add it here. So I'm just going to define these enthalpies one more time, just a name for them. The standard enthalpies. It's just a notation. Enthalpies of formation are labeled as. So there's two different ways to write them. The old way is this, delta H F with a circle here. And let's just remember what all these labels are. This is change. F means formation. And this means STP, standard temperature and pressure. Right? And the more modern way that and in fact I've gotten yelled at by peer reviewers and papers by writing it this way. There's the new way to do it now is where you put the F before the H. This is the new school way.
Stupid.
Yeah, I know, right? I have no idea why they made that change, but they did, and now people yell at me about it. I think the argument is that the enthalpy is a fixed concept, and it's really, you're measuring the difference from formation, and so the F modifies the change, not the enthalpy. It's a stupid argument, but whatever. I won't take off points either way. You can use either one. But when you see delta FH or delta HF, just remember that these are what we call formation enthalpies. They're the intrinsic heat contained in the molecule. Okay, so like an intrinsic amount of energy built into the molecule of heat energy. Right? And that's relative to these standard atoms and molecules. Right? Okay, so let's now think about temperature dependence. Right? We're seeing that these enthalpies of formation, right, the amount of energy stored within a single molecule is changing as a function of T. Sometimes it goes up, sometimes it goes down. All right, so we have to try to understand what are we measuring when that happens. What's actually occurring. Okay, so remember that H is a function of S, V, and P. All right, so we can always write, no it's not. This is N, I apologize, N. Constant pressure. And so we can always just go back to the first day of class, second day of class, and write the derivative of this, the total derivative, which is the derivative of H with respect to S. Let me start over. I apologize. Let's change this to T now. Sorry, we're in chemistry class. Chemistry flask and a bath. All right, so T is the better term here. So we have dH dt times dt plus dH dN plus dH dP dP. Okay, and we're gonna ignore this. This is chemical potential. We're gonna say this is 0 right now. And it turns out maybe we'll look at this more carefully. This term, the enthalpy difference as a function of pressure, this is usually very small. Enthalpy doesn't change much with pressure. Okay, so we're gonna just assume that the chemical potential is equal to 0 in this case. There's no exchange of material. Right, you're in equilibrium. Right, so we'll get through this. Right, so the important term of how the enthalpy changes is this temperature derivative. Okay, so what that says is that, right, remember that when this was U, total energy, we had this du dt as a function of t, ds, du ds, and we showed that du ds is the temperature, right? It's a response of the system. As you move h, how much does t change? Or in this case, if you move t, how much does h change, right? The slope tells you something about how, as you add heat to the system, how the temperature increases, or vice versa. Right? So this derivative here tells us this is the slope of h of t, the temperature, not time, h of t, which states either thing. One of you says is that states how much heat is required to raise T by 1 Kelvin. Right? So if we want to change T by 1, how much energy do we need to heat do we need to put into the system? This derivative tells us that. Right? And this derivative has a very special name. Right? So this is the derivative of enthalpy with respect to temperature at constant pressure. And this is what's called, we also call this C sub P. And the term for this is called the heat capacity. All right, so the heat capacity of this derivative, whatever it may be, it's going to be material dependent, tells us basically how willing the material is to store heat. Right? So think about it this way. All right? So as we start to feed energy into our system, there are two ways for the system to store that energy, right? One way for it to store that energy is in the internal motions of the system, right? If you have molecules, for instance, molecules can vibrate, they can rotate, they can move, but particularly they can vibrate and rotate. They can store energy inside of the internal motions of the molecule, right? So as you start to feed heat in, those molecules individually absorb some of that energy and they get kind of excited in their vibrations and stuff. The rest of the energy that doesn't go into that goes into the heat of the system, which is again the motion of the atoms pressing against the walls and the kinetic energy of the system, which we call heat, and that's what contributes to the temperature. All right, so if you have a material that has lots of different ways to absorb that energy without causing the kinetic energy of the material to increase, then it's going to have a large heat capacity because it requires you to put a lot of energy into the system to get the material to heat up. Right? It just absorbs that energy and holds on to it. It doesn't express it as a temperature. But then there are some materials, like for instance hydrogen gas or helium or argon, where argon's just a ball. The only thing a sphere can do is move X, Y, and Z, and that's just heat. That's just thermal heat. So an atom, for instance, has a very low heat capacity because it doesn't have any place to store that energy inside of it. Right? The only thing it can do is just go faster. Okay, so we have to think about the differences between those collective motions of the system and the PV work, if you will, right? Which is what really determines the temperature. So each material is going to have its own heat capacity. Right? So how do we use this to calculate different enthalpies at different temperatures? Well, it's very easy. We have, so let me just kind of write this over here. We have dH is equal to Cp dt. All we have to do is integrate both sides. So we'll start from an initial temperature to a final temperature, dH, which is the integral of Cp dt from T naught to Th. Yeah. Let me clean this up a little bit. I'm going to move this down here so I have some more space. Okay. Right, and then let's do the left-hand side of that integral. dH just integrates out to h, so this is h at the final temperature minus H at the initial temperature, your standard temperature. And that's equal to the integral from those temperatures of the heat capacity, which might be a function, dt. All right, so if we want to measure, this is what's called Kirchhoff's law. Right? If we want to measure, say, the enthalpy change, the heat change of vaporizing water at a different temperature than 298, we take the enthalpy of that vaporization at 298 and add to it, right? We add it to the other side here. Add to it the integral of the heat capacity of water and integrate over that heat capacity dt. Now, all right, so let me just take this and move it over. Good, got 30 minutes, fantastic. So we have H of TF minus our standard enthalpy is equal to Cp dt, integrated from our initial temperature to our final temperature. Right? If Cp is temperature independent, Cp is just a number, then delta H at a final temperature is equal to the standard enthalpy plus Cp times the change in temperature. Right? So that's a really easy formula. You might have learned that in Gen Chem, but this makes a big assumption. This assumes heat capacity is temperature independent. Right? Because Cp is just a number, I can factor it out of the integral. If Cp is just a number, it's not dependent on T, I can factor it out, and then I have the integral of Tf, T naught to Tf of dt, which is just delta T, change in temperature. Right? So we have to assume that heat capacity is temperature independent. For small t's, so I'll just say in general, for small delta t's, this is generally true. So dt small, it depends on the material, but let's say on the order of 10 to 50 Kelvin difference. This is generally true. Okay, but let's go back to our vaporization example. All right, I could go look up ATCT right now and figure this out, right? We just look up the enthalpies of formation. So let's go do that, right? But remember, so the enthalpy of this reaction, I wouldn't really call it a reaction. It's really vaporization. Let's call it HVAP, sorry. It's not really a reaction. Is the enthalpy of formation of the gas minus the enthalpy of formation of the liquid. Okay, so let's go look those numbers up really quickly. I'm not going to put it up on the screen. I'll just pull it up here. Actually, I'm going to pull it up on the screen. Let's just do it together. There we go. So to search for things on this website, there's a little species search bar. Let's just type in H2O. Wrong H2O. Right, and as you can see, there's lots of different choices for water. Right, so this is liquid water. Yeah, this is liquid water, gaseous water. I have no idea what this is. This is crystalline water, that's ice. This is para and ortho water. This is for real chemical physics nerds. Ortho, H2O actually has two isomers, ortho and para. I won't tell you why, but water actually has an isomer of itself, and they have different energies at 0 Kelvin. It's a really weird effect of water. Right, but anyway, all we have to do is plug in these numbers. So the liquid is the first one, it's minus 285.6 0.796 kilojoules per mole. And then we subtract, oh, sorry, that's the liquid one. I'm sorry. Sorry. The gas is first. I apologize. So gas is 240. It's the next one on the list. It's the second one on the list. It's 241.801 kilojoules per mole. And the liquid is minus 285.796 kilojoules per mole. Okay, so let's just roughly do that math. Right, this is basically minus 242 plus 286. Right, and that's 44 kilojoules per mole. Okay, so it says that in order to, there's a couple different ways to think about this, right? One says that it takes 44 kilojoules per mole to kick water out of its, at 298 Kelvin, to kick water out of its liquid phase and put it in the gas phase. Remember, these are at 298 at STP, standard temperature and pressure, right? So it takes 44 kilojoules per mole, or you can say that H2O, a box of H2O gas is 44 kilojoules per mole less stable than a box of H2O liquid at 298. Different ways to think about the same thing. But let's stop for a second and think about what's going on here, right? We have a thing of liquid, water at room temperature, right? That's not really when we often think about vaporization. It might be worth thinking about how much energy it takes to literally boil water, vaporize water at STP. We'll come back to that idea, what that might matter. But that's not when we think about water vaporizing, right? We think about water vaporizing at its boiling point. Right? So what is its boiling point? Well, it's not STP, it's 75 Celsius higher, right? Because it's at 100 C, not 25 C. Right? So it might be more useful to think about boiling, the enthalpy of boiling water at 313 or 323, whatever it is, instead of thinking about it at 298. Right? But is this number also valid at boiling? Or is it different at boiling? So that's a big issue. Now imagine you go even higher. You pressurize the bejesus out of that water. When you pressurize something, the boiling point increases. We'll see that next week. And so you could, well, maybe you have a big pressure cooker. If you've ever worked with a pressure cooker, you know this. When you have a pressure cooker and you pressurize some water, like you're making a stew or something like that, the boiling point of that liquid in that pressure cooker is much higher than 212 Fahrenheit or 100 C. It's like 300 degrees, right? Because you're compressing the system, and it increases the boiling temp point of it, right? And so it might be worth thinking about the energy requirements at the actual temperature that you're doing it at. And if we go to even higher pressures and go into these pressure-heavy situations where the boiling point becomes very high, this number probably doesn't even apply at all. So we'll have to see, we'll have to evaluate that, right? So let's evaluate it. Right? So what the question, of course, is that what is this at delta HVAP at 373.15 Kelvin. All right, so in order to do that, right, we need to refer back to Kirchhoff's law, which says that we need to, well, we have to integrate, we might have to integrate CP, but to calculate delta HVAP at the boiling point, we need to take the initial at 298 and add the heat capacity to it. Right, so where do we find the heat capacities for these things? Well, it turns out heat capacity is a really easy thing to measure. In fact, you're kind of doing that in your thermochemistry lab by using the electric heater. The electric heater provides a fixed amount of energy per unit time into your liquid, and you use that to calibrate the heat capacity effectively of your salt solution. So it's not too hard to measure heat capacities. You can do it with a calorimeter. So so now we're going to look at heat capacities. Right, and this brings me to my other resource on Canvas, which is the NIST webbook. Anyone ever used this website before? No one's ever used this before? This is an amazing website. So let's look up a molecule. All right, so let's look up H2O on this. All right, this is a repository of chemical information. All right, so here's water. There's different isotopes if you want to look at a different isotope. But the thing that NIST really has is all of the thermochemistry data for these molecules. So you see there's gas phase thermochemistry, that's enthalpies and entropies. Condensed phase, that's liquid and crystalline. There's phase change data on here. If you're interested in ions, there's ions. There's reaction enthalpies for things with water. There's spectra, chromatograph data, fluid properties. You can calculate the density of water at every temperature you can possibly imagine. Right? Lots of really cool stuff on here. But what we really want to look up are heat capacities, right? Because we want to calculate enthalpy at a different temperature. So we're going to need it for both the gas phase and the condensed phase. So let's look at the first one. All right, so the first thing that you see here are the enthalpies, and this is the standard entropies that one. We'll talk about this next week, this section right here, but there's also entropy, the standard entropy for that material at 298. But here's the enthalpy of the gas, the formation enthalpy. It's very close to the value that was on ATCT. The reason why I show you guys ATCT, because those are the hot off the press numbers. As you can see, these numbers are from 1984. Okay. Luckily, chemistry hasn't changed that much, but the precision has. Okay, so the numbers on ATCT are more precise and more modern. Right, but they're pretty close. The more interesting thing here is the gas phase heat capacity. Right, and almost every molecule has this. And one of the things you may notice is that here it lists a couple of different functions, here's CP. Here's the difference of the standard enthalpies between temperature and the standard temperature. So this is the standard enthalpy. So this is a function that tells you the difference of the enthalpies between 298 and your temperature. And here's the standard entropy. And what do we see? Well, it's just it looks like there's some numbers, A, B, C, D, E. But let's look. This is a constant, a linear function with temperature, a quadratic with temperature, a cubic, and then 1 over t squared. Right, where the t is temperature divided by 1,000. All right, and remember that I said that the enthalpy, right, the change in the enthalpy as you go from one temperature to another is the integral of the heat capacity. So what's the integral of A? AT. What's the integral of BT? DT? BT squared over 2. CT squared is CT cubed over 3. DT cubed is DT to the 4th over 4. E to the minus A over t squared is E over minus E over t. And then there's some couple coefficients under the constants of integration afterwards, okay? So these functions, so what happens is that the heat capacities, real heat capacities, they're temperature dependent functions, all right? They're the function of the temperature. And they're in standard written in this very, very simple form because it makes the integrals incredibly easy, right? If your heat capacity is a polynomial, it's really easy to integrate a polynomial, right? Because you don't have to do any math. You just add a power to the polynomial and divide by the number. Okay? So in order to calculate any enthalpy we want, all we need to do is just tabulate these numbers and calculate it at the temperature we want. All right, so let's just scroll down. You can see here that they give you two different tables of these constants, A through H. And they're defined at different temperature ranges because the heat capacity function isn't really a polynomial. So what they do is they take a reasonable chunk of the heat capacity function and approximate it to a simple polynomial. And then they split it up into different sections. Because there's not a lot of people doing work where they need to know the enthalpies at 500 and 6,000 Kelvin, right? You're either working at one or the other. So they split it up into two or into multiple chunks to give you more precision in the region that you care about. All right, so unfortunately, we want to look at things around 300 Kelvin. So these numbers are a little off, so we're just going to have to take these. Okay, so let me show you how you work with this data. All right, it's really easy. You can do it in Excel. The point is that every single one of these heat capacity functions is just these numbers times the temperature to some power. Okay, so all you need to do is put these numbers in Excel, and then have a table of your temperatures that you want to calculate it at, and then you just write the function down. Right? Very simple. Let's just show you. So we have to do this. So what we want to do, you can go ahead and move this over here. So we're going to have two molecules, H2O gas. We're going to have a value for A, B, C, D, E, F, and H. and then H2O liquid. There's going to be an A, B, C, E, oh sorry, A, B, C, D, E, and F, and H. Right? And all I need to do is just write these numbers down. So let's go do that. All right, so this is I'm just going to round them. 30.09, 6.8382, 6.7934, minus 2.534480, 0.082139, minus 250.0. And I don't need G for this, minus 249.264. Right. And then I'm just going to go ahead and do the heat capacity function for this. So let's set some temperatures. Let's do it at 298.15, 320, 350, 360, 373.15, 400, and 500. Okay, just some random ones. All right, and then now we're going to calculate the difference between the enthalpy at 298 and that temperature. Okay. And the way we do that is we're going to take, let's just scroll up again. Let's look at the formula one more time. So we want this formula right here. It won't let me select it, sorry. We want this enthalpy formula, the second one on the list here. So we're going to take A, which is A3, and we're going to multiply by the temperature, D3, and then we're going to take B, B4, sorry, this is B3, sorry. B3 times D3, B4 times D3 squared divided by 2 plus B5 times D3 over 3 divided by 3 plus B6 times D3 to the 4th power divided by 4 minus B7 divided by the temperature, D3, plus B8 plus minus B9. And I screwed it up. All right, so let's see what we did wrong here. I got it right the first time. Last class, B3, B4, B5 squared, D minus B7 plus B8 minus B9. What am I doing wrong here? Did I write the numbers down wrong? AT plus BT squared. Has anyone seen any problems yet? There should be 0, and it was 0 yesterday. Why is this not working now? Minus B9.
Did you miss any parentheses? That's what always gets me.
I don't think so. So I have B3 times the temperature, that's A times the temperature, B times the temperature squared over 2, C times the temperature cubed over 3, D times the temperature fourth over 4, minus E over T. Oh, I know the problem. So this is where we didn't get it. The temperatures are divided by 1,000. That's my problem. So what I'm going to do is this instead. And D3 divided by 1,000. Okay. All right, so we have to divide everything by 1,000. And then this changes to E3, 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 E3. Okay, there we go. So as you can see, and I'll just go ahead and move this down. All right, so what this is telling me is that, so this again is the enthalpy of formation of H2O gas. All right, so and this is the difference between the enthalpy at that temperature and the standard. So you can see at the standard temperature it's 0, basically 9 times 10 minus 5 is basically 0. And why are these numbers getting so much bigger? 52. Because these should be, oh, I think I know the problem. I think I screwed up the calculation. Okay. B6, E4, E4. Oh, yeah, I see the problem. B3. Yeah, it's moving. Sorry, I just have to do this. Okay. So I have to make sure that it doesn't change any of the labels. There we go. So fix all of these to constants. And then the last one. Okay, so that should fix the problem. Yeah, there we go. Okay, so what do we see? So this is the enthalpy of formation of the gas. Again, at 298, the difference is 0. And as you can see, it slowly climbs up to 6, to an extra higher 6, an extra 6, right? So that means that the enthalpy of formation of the gas is becoming increasingly more and more higher in energy as you start to add heat to it, right? And that should make sense, right? So basically, as you start to heat, that water can absorb begins to absorb some of that heat that's coming into its internal modes, its vibrations and its rotations and stuff. And you're seeing how much of that energy gets put into the molecule internally as you increase the temperature. So as we go to 298 to 500 Kelvin, the molecule has absorbed 7 kilojoules of that thermal energy to use for itself. Right? It's always there inside the molecule. Right? So this is like an extra 7 kilojoules a mole of stored energy, this heat inside the molecule. All right, so, but of course we need to do this relative to the liquid. Now that I know the problem, let's just do it really fast and then we'll finish up. So now we just need to do it for the liquid. The nice thing is, again, the equations are precisely the same. In fact, you'll see that for all of these, that pretty much every molecule in this database is precisely the same. 6060, 1523, 290, 96.413, 2474.455, 85326, 256, 285, 8304. And then all I need to do is just copy and paste my table of temperatures over here and enthalpies, and then just adjust my constants so that they're pointing to the right ones instead. So that's going to be B12, B13, B14, B15, B16, B17, B18. Okay. And then propagate that list down. Right? And as you can see, interestingly, the water, as you increase, proportionally adds more energy into its internal modes than the gas does. And that should make a little bit of sense, because the liquid water also has these collective motions. The hydrogen bonds themselves can store some energy, right? And so the system kind of collectively vibrates through those hydrogen bonds, allows it to store this extra energy internally through these hydrogen bonds, this extra potential energy in the liquid. And so therefore it has a higher heat capacity, a larger heat capacity, and therefore the enthalpy of formation increases more rapidly, because it can store more energy per unit temperature than the gas can. Okay, and so now to calculate, now we have everything we need for the enthalpy of vaporization. The only thing we don't have is the actual enthalpies at 298, which we just get from our tables. So the HF at 298, I'll just put it down here, right? We just have to scroll up to the top. Condensed phase is minus 285.830. And for the gas phase, let's just go back up and grab it. minus 241.826. So to get the enthalpy at some temperature, we take the difference and add it to the 298 temperature, right? Or the 298 enthalpy. Right, so these are our new enthalpies of formation for the gas. And we'll do it over here. This is B12, B11 plus F12. Right, so now I have enthalpies of formation of at every temperature. And so now if I want to calculate the enthalpy of vaporization, which is H2O liquid minus H2O to H2O gas, right? I just need to take the gas enthalpy, which is G3, and subtract from it the enthalpy for the liquid, which is G12, this list, right? And there's that number we saw earlier, 44 kilojoules per mole. This is at 298. And as we go down to 500 Kelvin, you can see the enthalpy of vaporization is starting to decrease. What this is saying now is that the difference between the stability of the gas and the liquid are starting to approach each other, right? The liquid is in some ways becoming, right? Let's see, the gas is becoming less stable as a function of temperature, right? Because it's becoming less negative. But the liquid is becoming even less stable as temperature increases, right? You've gone from 85 to 70, 285 to 270. Here you've only gone 6 kilojoules per mole. Here you've gone 15. All right, so what net happens is that now what's going on is that the gas stability and the liquid stability are starting to reach each other. All right, they're starting to get closer and closer. So what that means is that it takes less energy at higher temperature to vaporize the water, which is exactly what you would expect, right? You've got to put energy into boil. The one thing I want to stop, this was my last comment before the end, is that if we look at the boiling point of water, 373.15, it still says, right, it still says you need about 41 kilojoules per mole of energy to boil the water. Right? So why is it that when we get water at 373.15, that it boils spontaneously, right? You don't need to do anything to the water. If you just magically have a sample of water sitting out on the stand at 373.15, it just boils, right? It boils spontaneously. And so the question is, why is it that, right? And if you think about it, well, at 298, I only need an extra 4 kilojoules a mole of energy. That's not very much, right? It's like 1% of a bond. Right, so I just need to, at 298, that would mean that maybe I just need to sneeze on the damn thing and it'll boil at 298. But why is it that when I sneeze on it at 298, it doesn't do anything? There's a little bit of vapor pressure maybe. As you know, there's always, because we have humidity, right? There's some water vapor. So we know that some of the gas is in the vapor phase, liquid's in the vapor phase. At 298, we have humidity and dew point. But the enthalpy of vaporization doesn't really change in such a way that makes you think that there's something special happening at 373. Right? We know something special happens there. It goes from not boiling to boiling. Spontaneous vaporization occurs at 373. So enthalpy in this way, right, it tells us something about the energetics of the two states, but it doesn't tell us anything about the actual process occurring. Right? There's nothing here that tells us that 373 is some magical temperature at one bar, right? That it boils. We know that it does this. We know something magic happens here, and this number doesn't tell us. So we're missing something, right? There's something we're missing here, right? Which really tells us the right thing. It's getting easier to vaporize as you get hotter. But why is it at 373 that it magically starts to boil spontaneously? Okay, so we're going to have to start thinking about that, right? So next class we'll answer that question, right? We have one component we haven't answered yet. So we've looked at the heat of the system and how the system holds that energy internally, right? And how the internal energy of the bonds and the chemicals and the molecules and the atoms change. You go from one state to another. But what we haven't considered is how the heat and the entropy transfers from the inside to the outside. So the reason why we haven't been able to determine why nothing special here at 373 happens yet is because we haven't considered the entropy of the box and the exchanging environment yet. So when we start to think about how the entropy of the environment and the box change together, the total entropy, we'll start to realize that there's another term that we need to add into these energies, and then we'll see that something magic happens at 373. Okay, so something happens that isn't happening before, and then suddenly when you hit 373, it starts to kick in. Okay, so there's one more function, one more kind of measurement we need to make about our system to complete that picture. And when we do that, we're going to get Gibbs free energy, and that's going to tell us everything we need to know. Okay, so we're almost complete with our thermodynamic functions. Tuesday we'll have Gibbs. That'll give us our final answer. And then basically everything in the rest of this class is built around Gibbs. Right? So basically we'll have to start thinking about Gibbs energy and how to measure Gibbs energy. And that will lead us into phase equilibria and chemical equilibrium in the next couple of weeks. All right, guys, have a good one. I'll see some of you on Friday. Otherwise, I'll see you Tuesday.